Hey everybody, this is video 245. I'm Dr. Walker, and this video is called the time constant of a RC circuit. So the time constant of the RC circuit determines how quickly the capacitor charges and discharges. So the circuit is going to be constructed in such a way that the capacitor can release that energy in a certain amount of time. So the time constant is defined as RC. That means it's the resistance of that circuit times the capacitance of that circuit. It looks a little bit weird, but when you multiply these units of ohms and farads, you do get a unit equal to seconds. So the time constant is a certain amount of time. It's just a specific amount of time that is equal to the product of R and C. Let's look at it a little bit further. Let's look at the charge on a discharging capacitor. We've discussed this equation, this exponential, that shows how the charge varies with time. Now that we have defined RC as tau, the time constant, that's the Greek letter tau, we can replace tau here in the equation. So now our equation looks like this. Even though it looks like this is still the charge as a function of time. Tau is just a constant, right? It's just R times C. But now if we look at the graph, what this tells us is that after this specific amount of time equal to RC, then we're left with a certain percentage of our maximum charge. So let's see where this number comes from. What we have to do is we have to plug in time is equal to tau to see, okay, well, what is Q at time tau, right? You just plug in tau for T. So in this equation here, right here, in this equation, we're going to plug in tau right in here where T is. What you get when you have e to the negative tau over tau, you have e to the negative 1. That's what I have shown here. When you plug in time is equal to tau, you get e to the negative 1. If you plug in e to the negative 1 into your calculator, you get 0.368, which rounds to 0.37. So the time constant is a specific amount of time. After that amount of time passes, you're down to this percentage of your maximum charge. Let's also take a look at what happens after a long time. Now, this is kind of subjective. What is a long time? But in my opinion, if 10 time constants have passed or 10 tau has passed, that's a long time. The reason I say this is because if you plug in 10 tau for time into this equation right here, you plug in 10 tau into here, you get e to the negative 10 tau over tau. The tau cancels out, you're left with e to the negative 10 times your maximum charge. You plug in e to the negative 10 in your calculator, you get this very, very small number. So that means that after this amount of time has passed, which is going to be way off screen to the right here, you basically have zero charge left because you have just so little charge left. So that's what we mean by after a long time has passed. Although it is subjective, in this class we can say 10 tau has passed. That's a long time. You're basically down to zero charge as far as your discharging capacitor. So that is what I have written here. When time is much greater than tau, then the exponential is basically equal to 0. Okay, let's take a look here to summarize this time constant idea, the concept. If you have a short time constant, that means that tau, right, is a small number, then that means that you have a rapid decay. Because whatever the value for tau is, which is R times C, if that's a short number, a small amount of time, then that means that in this short amount of time, you're already down to 37% of your maximum charge or your maximum current. The equations are the same. after 3 time constants or after 10 time constants, you're basically down to 0 current. So if you have a long time constant, all I did is I stretched out this graph on the x-axis, and you can see that means that it's going to take longer for it to decay because this tau is bigger than this one, so it's going to take longer to get down to 37% and to get down to 0. So really remember this or understand this. The short time is a rapid decay. A long time constant is a slow decay. Okay, let's do a couple of questions. This is just a summary of what we just talked about. In a circuit with a large time constant, the capacitor charges very slowly. Is that true or false? So hopefully you said that was true. We just talked about that with a large time constant, you have a slow decay. You also have a slow growth. We could have done the same thing for the other graph when, let's say, when charge is growing, accumulating on that capacitor. Short time constant might look like this, but the long time constant, it might just take forever, right, to grow because the time constant is longer. So a long time constant is a slow decay. It's also a slow growth. Okay, let's look at the last question. Which capacitor discharges more quickly after the switch is closed? I'd like you to try this out by yourself. The first thing that you need to do is calculate the time constant for each of these circuits. Let's take a look. The time constant is equal to RC. We have R is 2 ohms and the capacitance is 6 microfarads. So 2 times 6 equals 12 microseconds. Remember, the time constant is an amount of time, it's in seconds. Over here we have 3 ohms and 5 microfarads, so the time constant is 3 times 5, which is 15 microseconds. So which one is going to discharge more quickly? The one that has the shortest time constant. So circuit A here had the shorter time constant. That means that capacitor A is going to discharge more quickly. It also means that if this were a charging capacitor circuit, that it would charge more quickly as well. That's it for this video. We have one more guided examples video. We will have a few more examples so that we can work with all of these new equations.